So, good morning. Can the remote participants hear me? Okay, I should probably join the meeting. Can someone say something, one from the remote participants?
Yeah, it's working.
It's working, great. Okay, we hear you as well, thanks. Okay, but maybe I should join the Teams meeting on my computer as well. So I can see the chat. Okay, then, yeah, let's start. And maybe let's move the camera a bit.
देख लो रिकॉर्ड कर रहा हूँ आपके सामने अगर हुआ नहीं तो मेरी फिर ब्लेम नहीं आता
But anyway, let's start. So, last time we finished the preach or the lecture about the responsibility of forensics experts, and we also concluded about the prosecutor's fallacy. So we ended that chapter, and then we started talking about the collection of persistent data, which is a very relevant area of IT forensics in practice. So we learned about the basics of hard disks, how do they look like, what structures do we have on them. So we talked about why not to open a hard disk drive. We talked about the partitioning, two versions of partition tables, and we managed to get until slide 42 as far as I remember, which is always a good number for computer scientists. Okay, so we talked about the partitioning schemes, and then we started with the topic of forensic duplication. So how should we do a forensic duplicate, and why don't we just copy files? And maybe that's a question that you should be able to answer now. Why don't we just copy all files? Normally, sometimes we do, but why don't we normally just copy all files on a hard disk drive for forensic investigation? Yes?
That would be read
Okay. Read errors and hidden data between partitions, right? Or more generally, all kinds of information that you don't see in the individual files. So there might be some things between the end of a file and the end of the corresponding storage block. Yeah, that's one important aspect. There is something else that we need to take care of when doing forensic copy. If we want to present the evidence in court, what will the court want to know? So you present some evidence that you got from the copy, which you made. Well, you want to be able to prove that the copy, so you want to be, yeah, you want to be able to prove that the copy has not been altered, right? So you want to have some evidence of the authenticity and integrity, and you do that, well, how do you do that?
YouTube.
Yes?
You are talking about authenticity and hash.
Right. So you compute a hash when you make the copy. So you have a hash of the original, and you can hash the copy later on and then compare the two. Will you normally just have one hash? Possible, but not necessarily ideal. So we mentioned, yes? Exactly. So if for some reason some part of that is altered, for example, to a read error, then you will want to have a lot of smaller hash values, hash values covering smaller parts of the hard disk just to be able to prove that the rest is correct. And then you can, of course, organize these not just in a list, but in in a tree. So not a hash tree or something like that. Okay, now so much about forensic duplication. And I always try to repeat a bit what we did last time. Of course, you all remember everything we did last time, but it just makes sure that I remember as well. Okay, so we talked about different types of images, and then we talked about the necessity of write blockers, and we had the distinction between hardware and software write blockers. And then the tools for the duplication process. And then in the end, we talked about live imaging. And I think we should continue here. I think we did not do that slide last time, because there are some special cases, and we cannot go into depth of all of these special cases. Some standard cases, some special cases are actually not that special anymore, like cloud infrastructures. So if you store a lot of your data in the cloud, then of course you might not, the forensic investigator might not even have access to the original hard disk. And if he has access to the hard disk where everything is stored, the data stored on that hard disk might belong to more than one client. So cloud forensics is actually a topic for itself. Well, there are cases of proprietary hardware. In many cases, the proprietary hardware is actually using standard components, just using non-standard interfaces, but you still have to deal with those. And then there is the case of damaged hardware. So in the beginning of the first lecture, we had those examples of flight data recorders and cockpit voice recorders from airplane crashes. And of course, they tend to be damaged to some extent. And it's important to be able to read data from those as well. So a lot of these cases have to be considered. We are now looking at the simpler special cases, and two of those are about some data that is just simply hidden from normal software. One is the host protected area, which is a hidden area at the end of a drive, and that can be used for special backup software, or also for storing a copy of the operating system if you want to reinstall the copy with some vendor-specific changes or additions, bloatware, whatever. It can be used for that purpose. It can also be used to store rootkits or some other malware or to hide some data. So that is something to consider. So it's just a question of the forensic software. Does it know how to access this host protected area? It's of course possible to do so. You just have to use the correct commands. And in that spirit, there's one more slide about that. There is something similar that we're going to talk about next, but here is basically how you detect those host protected areas. But I try to leave the practical aspects mostly to the tutorial, maybe just quickly. So you can look at the log file that is created during boot, and you can see that the operating system has detected a host protected area, and there are some tools mentioned here which can show you the host protected areas. Okay. So, sorry, I was just in the wrong window trying to move to the next slide, and the Teams window that did not work. Okay, another similar thing is the device configuration overlay, which is, in German we would say the same thing in green, das gleiche in grün. So also a hidden area, which is at the end of the storage area of a hard drive. And that can be used, for example, if a vendor ships several, a laptop vendor or computer vendor ships several different hard disk versions, the device configuration overlay can change the reported disk space to the operating system, so they all look the same. I don't know why this makes sense, but apparently it exists. So we should just know that exists. It's not really difficult or anything. It's just to know that these are there. Another example are virtual machines. So how to deal with a virtual machine, pretty simple, because you can just pause them, copy the entire state, and document that. So that's a lot simpler than having a computer where you have to consider what to do with that to not alter any data. So you should just be aware that virtual machines are pretty common nowadays, and you should have some knowledge about how to deal with them. Finally, there's the challenge of RAIDs. Does everyone know what a RAID is? So different RAID configurations, of course, exist, but the issue is always the same. Should you use the representation which is shown to the operating system, or should you just image all the individual drives? What is better? I mean, it's somehow mentioned on the slide. Yes? It's good. I'll just repeat that for the remote audience. So the guy here in the lecture hall said it depends on what type of RAID configuration you're using. If it's mirroring, so that would be RAID 1, you could just copy one of those because it's mirrored anyway, and that makes perfect sense. But there's Okay, so for RAID 0, basically, which is striping, you would copy both. Yes, another comment?
The question is, like, we don't know the RAID definition, and we don't just reconstruct the whole RAID.
No, that is actually the question, yeah. So should we...
In all of the RAID, we can go for easy checking. We just check if everything is the same, the data is the same, or if it's like, if this is not the case, we know it's either, the RAID 2.
Okay, I'm not familiar with RAID 2. Okay, what you're talking about is basically how to find out which version of the RAID system it is. Yeah. So you could do that just from looking at the data, yes. But maybe let me explain that from my perspective. So the issue is just abstracting from the specific RAID configuration. So the common one would be, I think, 0, 1, 5, and 6, I guess. But anyway, you could always copy each individual hard disk completely, so do a complete image of the individual hard disk, and then later on reconstruct the RAID content from those individual images. And that will work perfectly fine with a software RAID. With a hardware RAID, there are sometimes very vendor-specific proprietary formats. So you would need the exact same type of RAID controller, which would have to be working. So that would make it quite difficult. So it's probably easier to just use whatever content the RAID controller is showing to the operating system in the end. So in that way, you could just copy everything. So you could just copy the representation that is shown to the operating system, but not the individual hard drives. But of course, that means you're potentially losing some data, because there might have been something stored on the hard drives before the RAID was installed there. So some data might not be considered by the RAID. And there could have been some error in the RAID controller or the software, RAID software, so you might have missed something. But I don't actually know what practitioners would do here. I would guess that probably you would just use the first version, so you would just create an image of the volumes represented by the RAID controller. So just maybe quick recap for RAID. RAID 0 is striping, where you store half of the data on one hard disk, the other half of the data on the other hard disk, and obviously you don't just do the first half of all the data, but you do the block files, so you can read and write a lot faster, because you can read and write to both hard disks at once. And RAID 1 would be mirroring, where you just have a copy. And RAID 5 and 6 use more complex algorithms, where you can afford to lose 1 or 2 hard disks out of an arbitrary number. Okay. Any questions or comments about RAID? Basically, what I'm just trying to do here is to show you some potential complications which happen in practice when you cannot just copy one hard drive or one system. Another complication that we're going to deal with in a lot more depth later is encryption. And that is very common nowadays. So the question is, how do you deal with encrypted volumes? And the first question I would always ask about that, do you need access to the encrypted data? So do you need to somehow invest time into crypto or whatever? Or do you have an unencrypted backup, which would be a lot easier? Or is there some metadata? So if you, why could you have metadata if you have everything encrypted? What kind of metadata could that be? I was just about to say it, but maybe someone of you knows. Yes? A journal, but why would that be unencrypted when the rest of the hard disk is encrypted? Last, yeah, you could have timestamps, like the last time when the system was booted, yes. File types? Mm-hmm. Yeah, but why would you have access? I think the answer is correct, but why would you have access to the file sizes and types? You wouldn't have that. So I'm using, I have to admit, BitLocker on the system here, which is working fine for normal security requirements. And that would not give you any access to any of that information. But what could I be using? Yes. The size of the volume, of course. Yeah, you cannot have 2 terabytes of illegal content on a 100 gigabyte hard disk. That's the point. Yes. But that's not what I meant. What do you encrypt if you encrypt files on a hard disk? Maybe I gave it away. On a laptop, you will usually have full disk encryption, but there is also encryption on the file system level. So EFS encrypts individual files or directories. You can basically select that. And in that case, you would have the metadata. Or you could encrypt on an application level. So you could have PGP encrypted volumes or whatever encrypted zip files. And in those cases, there might be more metadata available. So that's what I mean with access to encrypted data. So the size of the encrypted volume of content, timestamps, file names, other file system metadata, if you encrypt individual files as is possible with EFS, for example. Okay, so assuming that access to the encrypted data is necessary, what could you do? What could you try? Any ideas? So say we have BitLocker or VeraCrypt or whatever encrypting an entire volume. And you want to get access to the content of the volume. What could you try? Come on, you must have some ideas. Yes? brute forcing the encryption key. I would not start with brute force of the encryption key usually, not directly. But probably you mean the same thing that I mean. So encryption key will usually be something like a 256-bit key. And so there are a lot of potential combinations, but yes? Exactly. Yeah, dictionary attack or brute force attack on a password, because if you derive a 256-bit AES key from the password 123, then it's easier to brute force the password until you get to 123. Depending on the, yes?
Enter passwords, there's always like, I would say, one step in the way. This is one way to speed it up by not doing the normal way, but just checking the, or like post the encryption key derived from the password.
Okay, very good question. How is the encryption key derived from the password? Does anyone know the answer? I mean, the details, of course, depend on the specific system that you're using, but in general, to derive a key, you use something called a key derivation function, or password-based key derivation function. But what's so special about these derivation functions? Yes? They might be one way. Yep. Does everyone know what a cryptographic hash function is? Okay. So one common way to derive a key from a password is that you take the password, hash the result, hash the password, and then in the end hash again and again and again. With some minor complications added, one of them being the addition of a salt. Everyone know what that is? So random value that basically prevents the creation of lookup tables for the passwords or for the hash function in general. So usually that will be hashing, adding a salt, and maybe doing one or two more operations, hash again. But the core aspect is hashing again and again to slow the process down. There are other functions which are specifically designed to use a lot of memory storage or whatever, but the basic one, which is commonly used, KDF2, would be just hashing over and over again and adding a salt. And for example, I'm not sure about WPA3 because it uses a different key derivation. WPA2 would use that, I think, with 4096 rounds of hashing all over again. And VeraCrypt, which is a common hard disk encryption system which uses password-based key derivation, uses, I think, something like 200,000 rounds for that. And that's what slows down the derivation of a key-free password. And that is intentional because that means that, for example, instead of a millisecond, you have to wait a second or something in that order of magnitude. But an attacker would probably need 1,000 years instead of 1 year. So that's the idea behind those password-based key derivation functions. And of course, you can throw more hardware at the problem. And for hash functions, we have those specific mining, Bitcoin mining systems and so on, which are very fast at computing hash values. Anyone have an idea of how many computations or how many SHA-256 computations they do per second? Thousands? Millions? Billions?
ये लोग
more like trillions actually currently. So there's a really specific hardware systems that do a lot of these computations per second. But still, if you use a reasonable password, you won't have a chance. So that would be one way to attack the encrypted volumes. This would not work on this computer here using BitLocker. Does anyone have an idea why? Yes?
Pata gobi, aloo beans.
What do you mean by that?
It's not encrypting files, it is encrypting the bits and bytes. So on the loaded.
Yeah, but that's the same for all sort of hard disk encryption software. They don't care about except for this encrypting file system. Okay, you're right about that. But the brute force attack is still the same principle. But on a computer with a TPM, you will not normally configure BitLocker to use password-based key derivation, but you will store the key in the TPM, the Trusted Platform module, and then you will have a pin for access to the TPM. So you have a chip that can actually do some sort of access control, verify the pin that you enter, and make sure that you cannot enter the pin more than 10 times. And after that, there is an additional wait time added, so brute force attacks get even more difficult. So that's sometimes the case that you store the key in hardware, and that makes these attacks more difficult in the end. Okay, what else could you do? In a practical scenario, as I said, we will go into more depth about that in a later lecture. So, I mean, decryption is always simple if you have the key. Where could you get the key? Yes? Yeah, timestamping, if you have some access to some system where you have at least access to metadata. But that would not necessarily, would be difficult to get access to the key. Unless you think of a scenario that I can't think of right now. There's another, yes? Yeah. Ask the person nicely. There's that nice XKCD comic about attacking a password. I hope all of you know XKCD. Okay, yeah, that's the one. I'm not going to talk about it now. If you just look for XKCD and password, I guess you would find it. It involves a wrench, and you should find it with that information. Anyway, so yeah, asking the person nicely or less nicely. But where else? So say I'm using hard disk encryption, and right now you want access to the content of this encrypted SSD. What could you do? And please don't try. Right now the system is up and running, so the key will be in the main memory. So, I mean, you could just walk to the computer, push me to the side, and try to get access. Yes? A side channel attack? Yeah, you could call it that. So what I could do is just lock my screen before you push me to the side, and then you need that sort of side channel attack. And for that, maybe I'll talk about that now. DMA attacks or cold boot attacks. That's what we're going to deal with within the lecture. So that basically means reading data from the main memory while circumventing the access control of the operating system. And that works obviously only if the system is still running, or at least in standby. If it's shut down for a while, then it becomes impossible. So that only works for a specific scenario, but it might work in these scenarios. Okay, and that's, yeah, or there might be a hardware token that you could still find. So the chance is not very good, So when I first gave lectures, it was quite uncommon for the general public to have encrypted devices. Nowadays, basically any Apple or Android smartphone, most of them at least, have encryption of the entire file system. And even for laptops, it's nowadays, I think, very common to use hard disk encryption, definitely in the corporate setting. So if you work for a company that has some sort of security awareness, then you will have hard disk encryption. One example is better key derivation functions. I mentioned that before, but you might still be lucky as an investigator if someone uses weak encryption. So there are, of course, proprietary systems, data formats, which just get encryption wrong. So there are still incompetent developers that use bad encryption or try to use their own homegrown algorithms. But in general, access to encrypted data has become a lot more difficult in recent years. Any more comments or questions so far?
Yeah.
Okay. So we talked about, in this chapter, just to sum it up briefly, we talked about preservation of evidence on hard disks and SSDs and other permanent or persistent storage media. And we mentioned that duplicates are very important and documentation is important. And write blockers are also important, so you don't change the original storage medium. We talked about some potential complications. The most important one probably, definitely being encryption nowadays, though those host protected areas and device configuration overlays, they exist and you should be aware that they exist, but there's not much more to them. So, what do we do with the preserved evidence? Okay, that's going to be a topic for a later lecture. Now we stick with persistent data, but we are moving up one layer or level and talk about file systems. And it's going to be about some general concepts in file systems, and we are going to talk more specifically about NTFS as one example of a file system which is common in the Windows world, though of course it's not the only file system that you might encounter in practice. What do we actually do with file systems? So if you have an understanding of file systems, what can you do with that? Maybe I'm going to answer that question. So you might be able to completely restore files that have been recently deleted. Why only recently? They might be overwritten if you wait for a certain time period or for a longer time period, exactly. But even after longer time periods, you might still be able to partially restore files, so that becomes a lot more challenging. And after we finished with this chapter, you should basically know what limitations there are to this partial restoration and under which circumstances this may work. Okay, interesting wording that I chose here. It's possible, or it might be possible to restore very small parts after a very long time. I'll explain later what I mean by that. It might be just a couple of hundred bytes in that case. It might be possible to restore metadata like file names and sizes even if the contents have been overwritten. And we are going to see why that is the case as well. And also, if you know how file systems work, you might be able to detect anomalies in case someone tried to fake evidence or to tamper with the file system. It's possible to, or it might be possible to reconstruct events. So when was a new file created within a file system? And the operating system will normally do all that for us if we want to access files, but with a deeper understanding of the file system, we can reconstruct the information or gather more information without using the operating system. And I think in the tutorial you will get to know some tools which you can use to actually do. There are a lot of file systems in use, but they usually have in common that we have some sort of hierarchical organization scheme. So, you know, the folder structure that is common both on Apple and Linux and Windows systems. And the data is then organized in directories usually, or folders, or whatever you want to call it. and files within those directories. There is user data and some structural data for managing the actual user data. Now, let's start with some terminology. We have seen that data on hard drives is organized in blocks, and they go by different names, unfortunately, like the file system blocks do as well. We're going to call them data storage blocks, at least most of the time. Sometimes we might forget that and give them a different name, but usually we will call them data storage blocks. And they are the smallest addressable unit of a storage medium. And we have seen that they are typically something like 512 or 4096 bytes or kilobytes large. They are also often referred to as sectors. They are created by low-level formatting of the storage medium. And last time we talked about why we have these blocks and don't just address individual bits or bytes. That's because of the addressing. So you would need to give a separate address to each byte, and that would be quite tedious. Now, the file system can just use those storage blocks and organize files in those blocks, or it can use larger blocks. Usually not smaller ones, that would once again be quite cumbersome, but you might combine 2 or 4 or 8 data storage blocks into one file system block, just because the file system can then use shorter addresses if you have larger blocks, and then you can have, or you can use a large hard drive with a certain given address length. In Windows, they are referred to as clusters, typically something like 1 kilobyte to 4 kilobyte. Questions or comments so far? Now, we have these addresses, and basically for the addressing scheme or how to find a block on a hard disk, we can use the partition address, which would mean the address relative to the beginning of the partition, or you could use the file system address, which is relative to the beginning of the file system, because the file system might not just start in the very first block of the partition. And we have the logical file address, which would be the address of the data block relative to the beginning of the file. So that's just the terminology. So it's just about the starting point, where do you start counting the blocks. And depending on that, you have the partition address if you start at the beginning of the partition, or the file system address, or the file address. Now, there are a lot of file systems around, and they all use, or many of those use slightly different terminology. So there is one author of one of the standard books for file system analysis, who tried to come up with an abstract model for file systems, and he then categorized the data within a file system into 5 categories, which we're going to talk about in the next couple of slides. And he did that basically to be able to compare different file systems and to describe the analysis procedures more abstractly. But it does not necessarily fit to all sized file systems perfectly. So that's something to be aware of, but we're still going to go through the abstract classification. And if you want to know more about that, there is a book, I think it's called File System Forensic Analysis by Carrier, and he's also a software programmer, so he developed a lot of program code for the SleuthKit, which is a standard forensic toolkit. Okay, so which categories are there? Firstly, file system data, which is general data about how the file system is organized. So at the beginning, so starting at the block number 0 of the file system, that might include the file system block length. So how many data storage block does a file system block have, or how many bytes does it have? How big is the file system overall? So how many bytes or how many blocks do you store in there? Which blocks are actually used or allocated? So which ones do belong to valid data and not just random data stored somewhere. And there might be references to additional data, like more metadata that can be used to access files more efficiently. We then have content data, which is the content. So if you have a file, you will have the metadata of that file, like how big is it and where is it stored, but the content data is the actual content of the file. And it's stored in those file system blocks, which are then made up of data storage blocks. And as we heard before, those file system blocks are called clusters in Windows and blocks in Linux. But the content data can, the file system blocks can either be allocated or not allocated. Allocated means they belong to a file, or unallocated. They don't belong to a file, at least from the perspective of the file system. They might still have content of a deleted file, in which case they would be unallocated. But yeah, the file system only cares for them if they are allocated. Metadata in a Carrier's model is location of the content data. General metadata is data about data. So in Carrier's model, that includes where is the actual content. So which blocks of the file system store the actual content, the file size and timestamps, like when was the file created, when it was at last accessed, when was it last changed, stuff like that. And examples for that include so-called inodes in Linux, directory entries in the FAT file allocation table, if you use FAT, or in NTFS, we're going to see that this information is stored in the MFT. But we'll get back to that later. Then we have file names. File names basically provide a reference between the name that the user uses, so test.txt, and the internal name. So the inode in systems like X3 or so, or the MFT entry in NTFS. Those file names will often be connected to a directory. So in a directory, you will have a list of the file names which belong to that directory. We then have application data of the file system, and that is data that is used for features that are not required for the core, like finding the data. The core of the file system is find the data on the hard disk, but there are other useful features like a journal, which can be helpful in case of a malfunction, or quota statistics, so which user uses how much data, stuff like that, and that is what Carrier calls application data of the file system. Any comments or questions so far? Yes? Actually, there are often several journals, but in essence, yes, so changes are noted in the journal. So if, for example, the power is cut during a write operation, the journal can be used to reconstruct either the previous or the final state that the file is supposed to get. So basically to ensure consistency. But there is more than one journal file, and we're going to see one example of that in NTFS, because NTFS is a file system that uses a journal. More questions or comments so far? I think it's going to make a lot more sense if we see a concrete example, which I'm afraid is going to be next week. So, how do you start if you want to analyze a file system? Well, one good starting point could be to start at the beginning. So usually within the first couple of data storage blocks of a partition, you will find the general information on the file system. That's what we, okay, once again on the wrong side. That's what we call the file system data. So that's where we could start the analysis. because it will show you what type the file system has. So there is going to be something like a header, which tells you is this NTFS or FAT or X3 or whatever. There will be pointers to further information about the file system, like files containing more information. Because the data there is in many cases essential to the functionality, so the system would not boot if this information was wrong. So if the system could not find the first couple of data blocks, then the system would not boot. So this is usually trustworthy information. What else could you look at? You could also look at information stored after the file system, and we had that before. You can use the volume stack because there might be some hidden information there. So that could be a starting point. Now, let's go through some functionalities of a file system, actually two functionalities of a file system. The core is you want to create files and you want to delete files. We also want to find files, but that's going to happen later. When you create a file, data blocks are allocated. What does that mean? And why does it say here, okay, it says here, they are marked assigned to the file system, but why does it say here that there is an allocation strategy? Why do we need a specific strategy? Yes? Yeah, right. Which blocks do we want to allocate? Is there a choice? Don't we just take the first one? Yes?
Yes, we could minimize, for example, segmentation.
Right. So you might want to minimize fragmentation. Pardon?
You can just use similar strategies as
Right. So there is a choice of strategies like do we actually just take the first few blocks that are available, or do we take a large section of consecutive blocks, which is specifically important if you have those hard or traditional hard disks with mechanics, where fragmentation of a file means that you have to move the read and write head physically. So that's going to take a couple of milliseconds each time. And that's why we want to minimize that. So there might be different strategies also for different usage scenarios. And that depends on the file system and the operating system. So there is actually a certain degree of freedom for the operating system, because for the file system to work, it's only important that you find those blocks later on. But the file system will also work if it's highly fragmented. So there is some choice for the operating system how to actually do that. So that's creation of the file, and the data blocks are allocated and they are marked as assigned. And those are actually two different processes, or to be more precise. Firstly, we have a data structure which says for each individual block, is it allocated or not? And then we have a second data structure which maps a file, metadata, to those blocks, to those specific blocks. So there would be one data structure saying which blocks are used and which ones are not used, and another data structure which says test.txt belongs or is stored in the following blocks. Why do we have two data structures for that? The second one would be sufficient because the information would be there, but so if you have 1 million files on the hard disk and you have the information for each file, which blocks this file uses, then you know, of course, which blocks are used. But, yes, exactly. If every time you wanted to create a new file, you had to go through the 1 million existing files and check which blocks they use. That would be very inefficient, so you usually have a second data structure which just has basically 1 bit if the block is assigned and 0 bit if it's not assigned. Now, when you delete a file, in many cases, actually the standard case, only the metadata are deleted or the metadata are not even deleted, so they might also just be marked as invalid. So that's what happens in NTFS by default. You will only basically store or change one flag which then says metadata entry number 4711 is now unused, or is now not valid anymore. And the actual data blocks are anyway usually only marked as unassigned, so they will not normally be overwritten. Why not? Yes? Right, just because of performance. So overwriting them would take time, and it's not normally a requirement. There are file systems which do that, or which allow that, but it's not normally something that users want. Okay, so the data blocks with the file content remain unchanged, but might of course be overwritten depending on the allocation strategy. They might be used for the next file that is created, or they might be used to 2 weeks later. Now, something might actually happen, and for that, we need to go back to the term of slack, which we've heard before. Slack means an area of the hard drive that is not seen, not normally used by the operating system, and we know disk slack, so an area that is not assigned to any partition, and we might count the device configuration overlay and the host protected area as slack as well. That's a matter of definition. But for file systems, there is something else, and that's called file slack. And how would that happen? Well, we have an area between the end of the file, EOF, where the last data byte of the file is stored, and at the end of the last file system block that belongs to the file. So the final allocated file system block, as it's called here. Of course, the actual file size is not normally going to be a multiple of 4096. In some cases it might be, but definitely not always. Assuming 4096 bytes blocks. Now, this file stack can be divided into so-called RAM stack and drive stack, and that's just terminology. So between end of file and the current data storage block, that would be called the RAM stack. So assume we have 512 bytes. So why do we assume? No, I have that example on the next slide. I will show you in the next slide. Why is it called RAM stack? It's called RAM stack because it used to be filled with data from the RAM by early DOS and Windows versions. So that's a historic thing that for some reason memory content was just dumped into that area. And then we have the drive stack, which is the storage area within the last file system block, but it's only the unused data storage blocks. So let's get to the one remark is that they are not normally overwritten when you create a new file. So they might contain fragments of old files. So say we have a data storage block size of 512 bytes and a file system block size of 4096 bytes, meaning that each file system block consists of 8 data storage blocks. And we have a text file with a size of 26 bytes. Now, the file stack is everything after the end of those 26 bytes to the end of the file system block. So that would be bytes 27 to 4096. And yes, I started counting at 1 here. Might be unintuitive, maybe. Not actually sure if it's unintuitive, but anyway, I did start counting at 1 here, which you see by the ending byte of 4096. We then have the RAM slack. That would be within the data storage block where the actual text file is located. And nowadays, it's not very likely that you will find any information in there. Who knows? But then there is the drive stack, and that would be bytes 513 to 4096, and those are normally not overwritten. And there you might still have some old data from a previous file. So there might have been a, say, test2.txt that was stored there previously and which was larger, and some of that information from that larger text file might still be there, even the file system block is now used by the new test.txt. Is that somehow clear? That's actually something that's quite nice to use as an exam question, because it's quite easy to ask that and to correct that, and to check correctness. So I would actually look at that so you know how that works. It's not really difficult, but okay, there are tools that look for that either look for information in the Slack or that actually allow you to store data in the Slack areas. Okay, so much about Slack. Now, if you want to access content data, and we are talking about difficult cases here. I mean, in the normal case, of course, you will just use your favorite file system explorer and double-click on the file. But that's not what we're talking about here. We are interested in analyzing content data if it's difficult, so usually for deleted files. So in the simple case, the metadata might still be available, because we learned that in many cases, the metadata are not actually deleted, but just marked as unused, just like the content data. So if the metadata is still available, then you just read the data blocks, so file system blocks to be precise, and store them into a new file, and then you can analyze that file. You can see if it's complete. So if it is complete, you can just open it in whatever tool created the file. Or you can analyze it, string search or search for hash values of parts of the content or whatever. So all that is possible. You have the full file or at least parts of the file, so that is definitely an option. Now it gets more difficult if the metadata is not available. So the situation now would be that someone stored some illegal content on a hard disk drive or some evidence on a hard disk drive, and then deleted the files, so the metadata was marked as unused, and then started creating new files, and then the metadata entry was overwritten. And now you're looking for evidence on that hard drive. So you're looking for content, but you don't know to which file any block used to belong. So you have a terabyte of data, and there might be something interesting in there. And for that, once again, you can use string search or search for parts of contents by doing partial hashes. Now, both is difficult. Why? So why is string search difficult? If you look for, say, what could there be? The string "I'm guilty!" exclamation mark on the hard disk. Why is that not as simple as it might sound? Yes? It's binary, yeah, and "I'm guilty!" exclamation mark is a text. So why is that a challenge? We can just translate between text and binary, right? Yes? Right, so which encoding is it? And there are several options. So actually ASCII and UTF, but not only UTF-16, but also UTF-8 and so on. So there are a couple of options. I'm traveling later, so I'm just going to recharge my power bank for okay. Okay, so that is one difficulty. What else? Now, admittedly, the next complication is a bit unusual and will not be an issue in many cases. But remember fragmentation. What could happen due to fragmentation if you look for "I'm guilty!" exclamation mark? Yes. Exactly. So you have millions of file system blocks, and one block contains I'm good, and another block which is somewhere at a completely different location on the hard disk says LT exclamation mark. So that might be the next challenge here. So, oh, I thought I had the challenges on the next slide, but actually I think it's a bit further ahead. Okay, anyway, so we had some of these challenges. Still, string search can be useful. You could look for email addresses, phone numbers, or typical headers, like the typical JPEG header content, if you look for images. And you can do that on the non-allocated data blocks, because for the allocated, you will usually know to which files they belong, so you only have to look through some of that. For the string search, just as a side note, there are optimized string search algorithms like Knuth, Morris Pratt, or Boyer-Muir. Has anyone here heard of those? Okay, basically they exploit structures in the string. So if you look for a string that is 20 A's in a row, and you found the AB at a certain position, then you know that you cannot have 20 A's in a row there. So you can move further along than just to the next slide. To put it simple, we will not go into details. Yeah, I don't think you even need to know the names, but they are common algorithms which can be used for an optimized string search. But it's not so common to have to do that in a forensic investigation, so it's not something that's going to be used every day. Now, for tools, as I said, mostly I'll try not to talk about the tools here in a lot of detail. Just to mention them, you could use a hex editor. You should be able to use a tool that allows to access data blocks or file system blocks. And you can use the strings tool to look for strings, like typical file management strings. As I mentioned before, fragmentation is a challenge. Encoding is a challenge. And also, if you have a multi-user system, assigning that evidence to a person might also be an issue. But you will probably be happy if you find anything at all anyway. Now, encoding, I mentioned that, or we mentioned that before. So all these are representations of the same string. That's actually an example I copied from I think it was from a book. Character sets compression is another issue. Forgot to mention that before, but do you know how Word documents are actually stored nowadays? Actually, those are, I think, zip files, at least some compressed file format, which contains the very strange, no, not so strange anymore. I think nowadays they use the open document format, but anyway, it is a zip file, so because of the compression, you will not find any strings from the Word document if you just look through the data storage blocks, because you would need to understand the zip format then to be able to decompress and then look for the strings. So compression is an issue. Encryption, as I said, on the file system level or the application level, or specific data structures, proprietary data structures and formats used by certain software. So once again, it's an issue of layers, like we had the magnetization layer, we had the file system layer, but now we also have additional application layers on top, like the compression and so on. So understanding that and understanding how the files might be formatted is challenging as well. One example here, this is looking for a credit card number, and here we have a typical hex editor output. And if you're looking for a specific card number here, it might be formatted in some unusual way. I think here it's not even too bad. So where is it? we do have the credit card number in reverse at some point here, and we have it in the right order above that. So, but both of these might happen. So that's just one example of a specific POS terminal. But as I said, the practical aspects are going to be dealt with in the tutorial. Now, another, and that's a very common method, is to use hash values for search. So, why would that be useful in real life? Now let's get back to, let's start with the simplest case. Actually, nothing has been deleted. The suspect just has 1 million files on their hard drive. Now, what's the challenge? Yes? Finding the file. Yeah. So in many practical cases, like the prosecutors that we are collaborating with, they look for child pornography images. And the perpetrators might have a lot of these images on their hard drive or just a few. And they might have 1 million images on their hard drive, of which 999,000 are completely harmless. But the prosecutors are looking for the few files which are not harmless. Now, they might have a database of, say, 5 million known images that they know exchanged commonly by the suspects or perpetrators. And of course, they will have hash values of those. And now you can just go through this hard drive and compute hash values of all files on that hard drive and compare those hash values with those contained in the database. You could also just compare the entire files, but that would take quite long. And a comparison of the hash values is actually enough. If you use a cryptographic hash function, then you can be certain that there is not going to be a random collision. So, very certain, not theoretically proven, but that there is going to be the possibility of a collision, but the probability is so low that it does not play an important role in practice. Now, anyway, we can compute the hash values of all the files on the hard disk and then compare them with the database. And because hash values are comparatively small, it's quite efficient to compare them with the content of the database. I mean, you know, indexing systems or indexing data structures in databases allow you very quick comparison. So that's not an issue. And here, now the process would be like generate a list of all hash values of all files, and then look for those using trap if you're just looking for one specific file. And if you're looking for multiple files, which is usually going to be the case, it's going to get a bit more complex, but still manageable. Now, that's a simple case.
Okay, go.
In practice, what often happens is the image is the same, but the hash value is not. How could that happen? Yes? Different file formats, exactly. Might be resized or recompressed or whatever. So there might be changes after which we as humans would still consider the image as the same image. But if you change one bit in the image itself or the metadata contained in the image file, like the image metadata and the file system metadata, then it's going to be a different hash value. So then you will have to use other methods. So it's not the only method that is going to be used in an investigation. But as I said, that's a simple case. Now the difficult case is we once again have deleted files, or we have files that might have been edited, so there might have been a change. And in both cases, we are probably interested in only parts, or we want to find parts of a file. So if we know the metadata is lost, so we have, say, perhaps 100 file system blocks in a row that belong to the same image, but then the next 500 file system blocks belong to a completely different file. And then we have another part of the image at another position on the hard disk. So in that case, you will only have partial files, and you can still use hash values, but the problem is you cannot just use a hash value of the entire file, because you don't have the entire file, or you don't know where the entire file is. Now, the idea is to just split the content into blocks, so the file content. Once again, we're calling these blocks, but they need not be data storage blocks or whatever. And we calculate hash values for blocks and not the entire file, because we don't have the entire file. And we search for hash values of the blocks in our image. Now, if you choose too small blocks, they might not say you as much as you might suspect at first, and might not be useful evidence in some cases. It depends. Why could there be blocks like 512 bytes which are completely useless? Yes. Too many false positives, but what could cause a false positive in, say, an image database? Yes? Yes? Images sharing the same data block, yeah, that could happen. Like bitmaps of a blue sky or whatever might be identical, and there might be just blue sky in one part of the image and the rest might be completely different. And there might also be headers, both for image and video file form actually be mostly identical, depending on how small the units are that you're looking at. So that could be an issue, or it could be text files where part of the text file is identical and part is not. So in identical wording, say they always have a standard disclaimer at the beginning of a text file, that does not necessarily help you. Now, looking at these hash values, if you added files, then we might run into an issue. Say we have these two file versions here, one being ABCDEFGHI, and the other one is ABXCDEFGH. And if your block boundaries are always after 3 of these units here, so ABC, new block, DEF, new block, GHI, new block, then you will not have any identical block after that insertion. So you would have ABX, CDE, FGH, so there is no identical block between those two files, even though the files themselves are mostly identical. Now, you can avoid that by shifting in smaller units, and you can use rolling hash functions for that. Rolling hash functions are optimized hash functions that basically do what the name says. So they would compute the hash value of ABC, next of BCD, and then of CDE. And update their state, so you don't have to do an entire recalculation of the rolling hash if you shift your window that you're looking at by a byte or a constant size. Now, these rolling hash functions are not cryptographic hash functions, they are just used for quick matching purposes, so they are sort of useful in certain data structures. They are not cryptographic evidence, but be able to find the evidence. That's admittedly a case that's not going to happen very often. Like if you have an image, someone will not just add some bytes to a JPEG image, but in a text file where you look and compare versions, that actually happens. Now, that is actually quite a lot of challenges that we have here. So we might have lost the metadata. If we have lost the metadata, we don't know where the content belongs. We have problems with encoding. We have problems with the matching in general. And we have a question here in the chat: are rolling hash functions the same as extended hash functions? I don't know. I've never heard the term extended hash functions.
तो ठीक हो
Does
फिर
anyone
भी।
know?
सुबह से तो बहुत
It happens that we have different terms for the same concept, but I've never heard of extended hash functions.
ये
So
पागल हो जाएगी, इस बीमार करेगी अपने
afraid I
आप को, और
can't
इसको
answer the
स्क्रीन पे
question. It
बैठ
seems
के।
neither can anyone else in the lecture hall. Sorry for that, but we're going to have that. It's a term used in crypto.
रात तक
Okay.
बात करोगे आपको भी
Any
आपको
cryptographers
लगेगा
here?
कूद के चलानी है कसम से इतना ठीक कर दूंगा
Standard hash functions. Yeah, I would normally just do a Google Scholar search, but
मैं कल ही ठीक कर देता
maybe
कल
we'll
मैं काफी वो था
postpone that to after the lecture. Or
हर जगह यार मेरे को डॉक्टर का मेरे को दिखाना है ये
okay,
मेरे
but in
मुझे
that
सही
case,
हो गया
then
है।
it's not the same. If it's a Merkle
दिख रहा है
Denver
ना, कलर भी
construction,
लगता है।
then
ये
might
नॉर्मली
be
है तो
some overlap in the concepts used, but rolling hash functions are not cryptographic hash functions. So yeah, okay, that's a good point. If it's a term used in crypto, then it's not going to be the same as rolling hash functions, because rolling hash functions offer no cryptographic security.
थैंक यू बेबी
सारा निकाल रही है मतलब easily निकल रहा
As far as I know, I mean, there might have been something that I missed, but I'm not aware of any rolling hash functions that offer security. Okay, now let's get, we're talking about problems that we're having, or challenges as we like to call them. Once again, mentioning encryption, we had that before, and we're going to talk about that once again later. Yeah, encryption could happen at the application level. You PGP encrypt a file, or you use encrypted zip archives. We have file system encryption, or hardware encryption, or whole disk encryption, or whatever. And that is also a challenge in analyzing content data, but it's going to be a challenge for later chapters. Now, looking at metadata, now, just like the content data, the metadata can be used or unused, or we call it valid or invalid. And deletion normally means that the metadata will be marked as unused or will be released. But there are still tools that can find metadata entries for different file systems. And ILS and ISTEP are tools that you will find in the SnoopKit for analysis of some file systems, where you can actually find the metadata with those. Okay, what else could you do with metadata? You could do timelining. Like the metadata is stored per file. So the organization criterion is the file name. Yeah, in the end it's a file name. But you could also look at all the timestamps contained in the metadata and create a timeline to analyze at which point in time which files were accessed and modified. Assuming the data about last access is available, doesn't have to be available on all operating systems, but in many cases it is available. So in that case, you could do a timeline of all changes in the file system. And of course, you can match that up with other evidence that you have. If you have some log files about an ongoing attack, then it's not just going to be the file system that you include in the timeline, but all other evidence that you find. Of course, file timestamps could have been modified by an attacker, so that's something to look out for. What else could you do? You could, of course, look at the data blocks if you have the metadata and analyze the data blocks. But we mentioned that before. Why do I have that again on this slide? Yeah, so that is assuming you have access to the metadata. For timelining, there are tools like Log2Timeline, which can create these timelines, and that's what I mentioned before. You could combine all sorts of evidence, and we're going to talk about these sorts of evidence later on, like events log, registry databases, and so on. You can basically include all that in the timeline and visualize that using tools like GNU-Blot. Not going to go into much detail there. What else could you analyze? Now, file names might also be useful, and file names might still be available even if the other metadata is not. So when you delete a file, Depending on the specific file system, either the management data structure is wholly marked as unused, but the exactly, but the data is still there. So the file name and the reference to the metadata are preserved, and then it's very easy to reconstruct the data because if the content is still there, you can just use the metadata, which is just marked as unused. We mentioned that before. Or it's possible that the metadata, so the data which tells you which content blocks belong to the file, that data might be deleted. Or the reference to that data might be deleted, but the file name is still there. So you have the directory data structure, which has the file name, which is marked as no longer valid. And that data is there, but the pointer to the metadata is not there. So then it's interesting to look at the file name and guess the corresponding metadata entry, or to just read information from the file name. So if the file name is something conspicuous, that might be useful in itself. So different versions, either the file name and the metadata is still available and linked, or the file name is possibly still there, but the reference to the metadata is lost, or the metadata itself is already lost as well. So you can look for keywords like bomb within the file name if you have that information available. So to put it short, file names might still be there and you could look through them. Now, next we have a journaling file system. So as we mentioned before, we talked about that. Recent modifications are written to the journal. So after a crash, so if the power is lost or whatever, then it's easier to recover the data using that journal. And when you boot up the system, the journal is read, and if changes in the journal have not been performed yet, then that can happen afterwards, and you can use tools from the sleuthkit to analyze the journals. But we're also going to look at the journals in more detail, because the next part of the chapter is actually more concrete, and I guess that might make it a bit more interesting to see one specific file system. I selected NTFS for that. Could have been any other file system because a lot of the concepts overlap. But no, we are using NTFS for the remainder of the chapter. But are there any questions so far? Anything about the general concepts of file systems? Okay, so that does not seem to be the case, so we're going to continue with NTFS, and we're going to talk about NTFS in general, and the core concept in NTFS is basically the master file table, which is a large data structure that stores all the metadata of the files, and it contains attributes for the files. But we're also going to look at the metadata files of the file system, and we're going to look at deletion and creation of files, and we're going to see something about alternate data streams. Now, NTFS stands for New Technologies File System, though it is from the last millennium, actually. It has been the default file system on Microsoft operating systems since Windows NT and 2000. And on desktop computers, I think it's still the most common file system. So maybe I should have said desktop and laptop computers here. If you count smartphones, then apparently not. So NTFS supports large volumes in theory, 2 to the 64 minus 1 clusters. On Windows XP, the actual implemented size was a maximum of 16 terabytes. Documentation is a bit shady, so it's unclear, but unlikely that this limitation still applies to current Windows versions, because 16 terabyte hard drives are actually possible nowadays. But documentation is not so good.
उसमें
put it
हम बातें
mildly.
करता चुप चुप बता
So, what does Microsoft say about NTFS? It was designed to be reliable, secure, supporting large storage media, and 16 terabytes
इसने
was
सारे
very
टॉपिक्स
big
में भेज दिए
25 years
एग्जाम से
ago.
पहले मेरा एग्जाम था 14 तारीख को
And
तो
it's
10
supposed to be
तारीख को
scalable.
टॉपिक भेज देते
It is
हैं इधर भेज
more complex than its predecessor had. And as I mentioned before, we don't have an official specification how it works in detail, but the principles are known and have been reverse engineered. And of course, there is some documentation available by Microsoft, so we know how it works in general. Like some other file systems, the core idea is that everything is a file, so every byte of the file system belongs to a file. Is there an error here on this slide? An NTFS file system, so a new technology file system. Can discuss that. Maybe I deserve some chocolate for spotting that. So file system data and all metadata are stored in files, and the file system starts with cluster 0, which is where the boot sector begins. Default cluster sizes, you don't have to learn that. Between 512 bytes and 4 kilobytes. It's a journaling file system. All changes to files are logged in a journal, though it's not all the content that is also stored in the journal. So if you store a 5 gigabyte movie, then it does not just create a 5 gigabyte journal before that. But it will store the operation as such in the journal. So if it's copying a file, then it will have that information in the journal that the file is being copied. So when you reboot the system, then the operations from the journal are then executed. Log files are, and that's what I mentioned before, there are 2 log files. The NTFS journal file, the log file records changes to metadata, and the USN update sequence number journal, that's what the USN stands for. It has some higher level information about changes to the volume. It's not required for the core functionality of NTFS, but for indexing. But actually, I'm not sure if I have more information about the journals in the slides. I might look that up and add something for the next chapter, because you also had a question about the journals. And I've actually never looked into the details of the journals myself, so that might be something for next week. Now, yeah, okay. We can do with a quick overview. An NTFS volume consists of a boot sector and the master file table, followed by the file system data, and there's also a copy of the master file table. Exactly, and that's basically it. So the boot sector has information about the layout of the volume in general. This is about the structure of the file system, and it has the boot code, so the code which is executed on boot up of the system. The master file table is a huge table that contains all the information that you need to retrieve files, so basically all the metadata. The file system data is all the data not included in the MFT, and we have a backup copy of some MFT entries. So in an image, we have a partitioned hard drive, and on this first partition here, we have NTFS, an NTFS file system, with a copy of the boot sector and the actual file system itself. And the actual file system itself then as the files, yep. And in the files, there is also the MFT, because everything is the files of the MFT itself is also a file. And because it is relatively complex, and we are running out of time today, we will restart at this slide next time. And so that's slide number 39. And for today, I guess we are finished, unless there are questions or comments so far. There is the tutorial this afternoon, but nothing further from me. So thanks for paying attention and have a nice day.